Hi, my name is Andy Tran,
And I am Fanny Zhu.
and together we implemented a Burroughs-Wheeler transform DNA sequence aligner. Before we go into detail what exactly a Burroughs-Wheeler transform is, it's important to note the motivations behind this project. So as you guys may know that big data is the craze nowadays, and for us, bioinformatic big data is what we're really interested in. So our human genome, which is the DNA that contains all the information of our health, is essentially 4 characters, ATCG, and it's essentially 3 billion bases make up each and every one of us. And in order to find if there's a key disease-causing mutations, we have to search through this huge text file. And to be able to analyze huge text sequences like this, it's very time-intensive and computationally heavy process. So in order to make this process much more easier, we're trying to think of ways to improve it by using string compression algorithms or transformation algorithms to make a string much more amenable to be searched. And one key function is Burroughs-Wheeler transformation,
Also known as BWT for short. And so BWT takes in a string and adds a marker at the very end. We have chosen this marker to be the $sign. So the way that BWT transforms the string is that every possible cyclic rotations of the string is generated in a matrix. These rotations are then sorted in alphabetical order, and finally, the output is simply the last column of the matrix. A faster way to do this is actually using a suffix array. So the suffix of each cyclic rotation of the string is stored in an array. Then an index array is generated to be used to construct the BWT transform string. Now I'm going to show you how to run the BWT function in our program. First, you have to change your directory to the folder containing our code. Then you would want to type in python bwt.py and then the string that you are trying to transform. So let's just say banana. As you can see, the output string helps group similar characters together. A better use for this is for DNA sequences. So here you can see that the output groups all the similar characters again.
and you can see a Burroughs-Wheeler transform DNA sequence groups all these similar characters together, and that's really what's the powerful driving force behind allowing us to search these DNA sequences much more easily. So mapping DNA sequences or trying to align whether a disease-causing mutation is found in your reference sequence is a much more efficient process. So what we've done is after implementing BWT, we also implemented an aligner. So in our aligner, we take in an input sequence. In this slide, we're just showing an input sequence of banana, and say we're trying to look for a query of Anna. What we do is Burroughs-Wheeler transform our input sequence banana, and then we would find the index at which it occurs. So Fanny would demonstrate how this actually works.
So the way that we have implemented the aligner function is taken an input of a text file. And so here we have an example text file containing the chromosome 1 of a yeast. And say that we would want to find the gene CATAAA. We would get an output showing us how many matches were found to our query. You can see that your query is highlighted. We also implemented our program to also generate an output text file for easier viewing. So as you can see here, again, you can see the number of matches found and also the indices at which the matches were found.
So after creating this, now what? So essentially, if we use BWT to have a very efficient aligner to find exact matches, if we have exact sequence that we're looking for in the genome. But a lot of times, DNA sequencing quality is poor, or at times there's genuinely mutations that may cause different bases to misalign. And in that case, a current function would fail because it only does exact matching. So we would implement a function that allows for mismatches, and also the next steps we can optimize different sort functions that we've utilized and optimize even our fundamental implementation of Burroughs-Wheeler transform. We can explore other data structures. But for now, this is our Burroughs-Wheeler DNA sequencing aligner, and thanks for all your time.